Hello everyone. If you're a designer and you're thinking, oh no, this doesn't sound like it's for me, it is for you as well, promise. I'm a designer as well. I'm just going to test the audio. You did hear that a minute ago if you're wondering what it was. It was Oscar. So now we know the audio is working. So I'm Laura Kalbag, and as I said, I work for Stately. If you want the slides or links to anything during this talk, you can get them at noti.st/LauraKalbag/JICHBT. I will also have this QR code again at the end. So I've been working in a whole variety of tech teams for the last 15 years or so. I've worked in design, I've worked in dev, I've managed projects, I've worked for managers on projects. And one of my biggest pet peeves in all of these teams is this separation that is created between all of our areas of expertise, when realistically there is so much overlap in what we do. We're continually doing other people's work. A designer will make decisions that impact engineering. Engineers frequently make design decisions because they're trying to fill in the gaps in the information that they've been given. And project managers do the same as well. And we're all constantly passing documents around to try to get feedback and requirements from each other. And sure, there are better ways we can communicate, processes we can employ. And yes, sometimes it's always better if we set our egos aside a little bit. But sometimes we just need tools to help us get there faster. And because I'm all about, having been from both a design and development background, uniting designers and developers, I want to show you today a cool little demo, a little app that really unites those things. And we're going to talk about managing your application logic. So let's start off with some issues that we find around state management. So complexity. Basically, the bigger the app, the harder it is to manage state. Like even the smallest feature can introduce an astounding amount of complexity for such a small feature. We have data flow. Passing data between different components can get very complicated and very hard to follow around your app. We have concurrency. So when different components are trying to interact with the same state simultaneously, that can get really tricky. And of course, testing and debugging, because the more states you have, the much harder it is to isolate and reproduce your state-specific issues. And if you've used a lot of Booleans for your state, then you will certainly know what I'm talking about. And let's be honest, a lot of the time, not even just our application logic, but how everything works is essentially stored in an engineer's head somewhere. If you're lucky, it's multiple engineers. But it's not really the most convenient place to have all your logic stored, especially if someone goes out of office or goes off sick or decides to quit. It can all be a little bit fragile, and that can make you lose sleep at night. I mean, if you're as anxious as me, that's for sure. Speaking of losing sleep at night, I decided to build a white noise machine app. And this is because my dog, who you saw at the beginning, Oscar, he hates fireworks and thunderstorms, and it makes him really anxious. And so we got one of these physical white noise machines, which anyone who has babies might be familiar with. And it's just really cool. It produces white noise. It has a light. It's really helpful. And I was like, well, maybe that would be a cool app to make for a demo. So I thought about the states that I might want to use in a white noise machine app. Excuse my terrible handwriting. So we've got on and off. We've got playing audio, pausing audio. We've got sounds, and I want multiple sounds because all the best white noise machines have multiple sounds. So that would be white noise and waves and a fan maybe. And colored lights. I love colored lights. If I get to do something on the web, I'm going to stick color in it. And so I want to have some yellow and some green and some blue. And I'll probably want to have control over making the volume go up or down. So this is already getting really complicated for something that's just really basic demo. So what am I going to recommend for this? Well, the clue is in the title of my talk. This is a finite state machine. So raise your hand and keep your hand up if you are familiar with state machines. Now put your hand down if you learned about state machines studying computer science. Yeah, I thought so. But still, that's really cool, the amount of you that didn't learn about it in computer science and still do. So a finite state machine is essentially a model that can only be in one state at a time. So the states we have here are paused and playing. Usually the example that state machines have, the one you'll find on like Wikipedia and stuff, is a coin-operated turnstile. I don't know anyone who uses those anymore, so I've gone with this instead. And so you have your states, and you can move from one state to another in response to an input, in this case, in response to an event. And so when we go from paused, we go through the play event, and we transition to the playing state. And so from playing, we can hit the pause event and transition back to paused. That is a finite state machine. And a very important little icon in a finite state machine is this funky little arrow here. So there's like a little blob with an arrow coming out of it, and it is pointing at our initial state. So this is telling our state machine where to start. State machines are also a really great visual representation of your code. So it'll tell you what your code should be doing. So I'm going to create this state machine for my app. Now, despite the front-endiness of my examples, state machines can be used anywhere in your stack, and I'll show you some examples for that a bit later. So I'm going to start off by creating a state machine, and I'm going to have my initial state is going to be power off, and then I'm going to toggle the power, that's my event, and then power on. Oh, sorry, the air is very dry up here. And then we're going to add some actions. These are your fire and forget side effects. So we're going to add for power off, we have an entry action of hide buttons. And then for power on, we have an entry action, show buttons. So we're going to hide buttons when the power is off. When we go into power on, we're going to show the buttons. And when we exit power on, we'll hide the buttons again. So far, this is a very finite state machine. Sorry. So next we're going to add some state charts features. So state charts are a visual extension to state machines that help us model more complex logic. So first up, this is going to be hierarchy, parent and child states. And so inside our power on state, we want some different sound options. So we're going to have our white noise machine, sound. We're going to toggle the sound to go to waves, toggle the sound again to go to fan, and then toggle the sound to go back to white noise. So we can see how that works. Quite like our pause and playing. And of course, each child state also needs its own initial state to say where to enter. And then we have another useful feature of state charts is the ability to have concurrency. So basically, we can have parallel states. So I'll make my sounds like children of a parent sound state. It's going to make a child of power on. That is going to be sound. It's my sound state. And then I'm going to paste in, there we go. Oh. Made that visible. And so inside sound, I have my white noise, waves, and fan sound. And I'm also going to add a light state and a volume state. And these are currently unreachable. Can't get to them. There's no transition that takes us there until I change the state type to parallel. So now everything in my sound state and my volume state and my light state can be active simultaneously. Next, I'll add some actions to my sound states. So I'm going to add child states, actions first. To my white noise child state, there we go, we've got entry action, we're going to change to noise. And when we enter the waves state, I'm going to change to waves. And then when we get to our fan state, I'm going to change to fan. And for our light, lots of rearranging. Got to make it pretty at the same time, make it easier to read. We've got our light off. That's our initial state. for lights, and then you can remove the color. Then we're going to toggle our light. Love a toggle, very useful, a button that does one thing. And we're going to yellow, and what were the other colors? We're going to have to toggle the light to blue. Is it blue next? Yeah. And then toggle our light event back to a green state. And then a final toggle, take it back to being light off. So this is covering quite a lot of our complexity just in this little diagram. I'm going to also add my entry action. So when I get into the yellow state, I want to fire off an action that sets yellow. And then I want to fire off an action blue that sets blue. You'll never guess what action I'm going to do on the green one. Yep, set purple. No, green. Now I want to show you self-transitions. Now, self-transitions are transitions that can fire off actions but then return straight away to the same state. And this is really useful for updating your context. So we'll do this for volume up and volume down on our volume state. I'm going to add, is that nice and big? Yeah. So we'll go volume up, event. And that has to be positioned above because I love semantics. And the volume down event will go below. And we'll add some actions. So when we hit the volume up event, we're going to fire off a volume up action. And the same volume down, except it will be volume down. There we go. We also want to add guards for our events because you don't want to be able to infinitely go volume up or infinitely go volume down. So here we're going to add a guard, which is a kind of type of conditional, which says if it is not at the maximum volume, then you can do the volume up. And if it is not at the minimum volume, then you can do volume down. And so when you hit these events, they'll only transition and only update the context if it meets that condition. So now we have conditional logic as well. So another concept that works really well with state charts is the actor model. And that is where everything in your system is an actor. And an actor can send and receive events and change its behavior based upon those events. And we can use that to make our logic a lot more modular and a lot more maintainable. You don't have to have giant state machines that represent the entirety of your app. You can have lots of little state charts that can talk to each other. And so basically, when any state chart is running, it becomes an actor. So I'm going to make the audio player for the white noise machine into its own actor. And this is a useful approach because if you think about something like an audio player, you might want to change the functionality of that in the future. You might want to add, I don't know, some kind of cool Bluetooth functionality. You might want to add some sort of modulation or something like that. And so if you have that separate, it's easy to maintain without having to touch your main machine. And so I'm going to invoke that actor when we power on. And so I'm going to go to the power on state. I'm going to add my invoked actor. Tiny, tiny text. A bit bigger there. I'm going to call it audio player. You can't quite see it right now, but if I hit the edit button, there we go. Very importantly, I want to also give that an ID of audio player. And then when we enter the power on state, I'm going to use a very special type of event, an action, which is called a send to action. So that's going to send the action very specifically to the audio player actor, and it's going to send an instruction to play. And I'm going to do the same for when I exit the power on state. I'm going to add an action, and that is going to send to the audio player. And I'm going to call that pause. It's pause and play because of the web audio API. It's not really a big fan of the word stop. So having a state chart that is also executable code means you can do really cool things like simulating your machine. So I can walk through the machine as it will work live. I just need to rearrange it so it's a bit easier for you to see first. Even if you can't read the text, you'll get the idea, I suppose. So the blues events represent the events that you can hit when you're in that current state. So when I go into power on, you see there's a lot of different buttons available to me. But it also means I can very easily spot an issue. So what I forgot to do here was I forgot to add a toggle that would go back to power off. So what I could do is I could just go back and add a toggle power off. So that needs to be an ordinary state, ordinary event, and that is going to be called toggle power. And now if I go to simulate my machine, I can toggle the power on, I can toggle the power off, I can toggle the power on, I can toggle the power off, and it all works. So as I said earlier, state charts can be used anywhere in your stack. And hopefully now you can see a little bit of the potential of state machines for your UI. And here's just an example of some back-end workflows that you could use for state machines for. So here's an event-based actor, which is like a common example of container environments, where some of your services, or also known as actors, might not be exposed via a resource URI and are then accessible by submitting an event to the underlying container events manager. Here's patient onboarding, where we might want to invoke 3 actors simultaneously. Here's a serverless workflow where you need to integrate with like an external microservice to perform a credit check. You know, that really wholesome thing of performing a credit check. And through this demo, you might be thinking, oh, wow, there's not actually much code here, and this is really easy to understand, and I didn't even have to explain that much. And maybe even the coworker I have that never gets anything might actually understand this. And this is because diagrams are great. There's visual representation of code, there's clear communication, it's also really easy to collaborate and easy to spot errors, which is great for documentation, and all of this helps with better planning and organization. And state charts provide all of the benefits of diagrams, but as executable code. So having your application logic be both visual and executable means it makes really good living documentation. It's a logical source of truth because everybody understands it and it can be kept always up to date. So going back to the problems that we have in software development, we have the modular and hierarchical structures and state charts. They really help with handling all that complexity better. The explicitness and the clarity that we've got in these diagrams make it much easier to understand. The visual representation is like really good for internal documentation. So imagine like making a PR and you can see visually a diagram that shows the difference between a feature that's been added through its states and its events. And we have a really clear structure for testing and debugging. So I'm going to skip ahead because you don't want to see me adding more actions and events, but I've added a description to my machine to make it easier to understand, and I've just added some fun colors, which will also make it easier to point out certain elements of the machine when I'm talking to my team. And I've also added a set volume action, which is in my power on. So right there, it's an entry action. That will set the volume because I want to make sure that I've got it set to a standard volume when someone turns the white noise machine on. And to my machine's context, I've added a volume value, and I have given it a key, and I've added it an initial value of 5. And with special like XState actions, some of which I showed you earlier, I've added assign actions to my volume up and volume down. And so this will allow me to change the context or update the context every time the volume up and volume down events are triggered. So if I go to export all of this as code, you'll be able to see that pretty much this whole machine can be expressed as a JavaScript object. So it's actually really easy to read in code itself if you needed to do that or wanted to do that or needed to update it or interact with it as code. And right at the end, you can see where we can add our implementation details for our actions and our actors. There's our actions, and there's our actors, and there are our guards. So this is all JavaScript that's formatted for XState, which is a free and open JavaScript and TypeScript library for state machines and state charts. I would recommend you check it out on GitHub. You can get the link at the end. So now I'm going to export that code to StackBlitz, which will help set me up with a little demo app that will just walk me through my machine states. Come on, StackBlitz. And this is pretty much like the simulate mode, except you're not seeing it represented. You can just see the events that you can interact with. And if I jump to a version of the machine that I made earlier, a little demo in StackBlitz, I've got my machine here that's exactly the same, but you can see that I've used in the index.js file, I've used this machine.provide method with XState, and I've used that to provide the implementations for my actions and for my actors and for my guards. And if I play my machine, so this is where the audio comes in, big flash of white, power on. There we go, we have white noise, and we have waves. And we can turn the volume down. It's updated the context in the top corner, and you can turn the volume up. And you can turn it back down again. And then we can switch back to a different sound. Yep, fan. It's not annoying at all. I don't know why anyone likes fans. Back to white noise. And then concurrency. Our light is working at the same time as our sound, and we're switching between the light and the sound. And it's all updating, no problem. A nice green wave sound, and then we turn our power off, and the light is still on. So that's a problem that I need to fix. Because I've got my logic separate from my implementations, I can return to my state machine, and I have, do you remember the action that I added to remove the color on the light off state? So I'm going to copy that, and I'm going to add that as an action when you exit the light state. So when we exit the light state from power on to power off, that should enable me to make that work. So I'm going to copy my machine back to the machine.js file. Easy to override that. And save it. And now when I run my machine again, fingers crossed, power on. There we go. We got waves and light. That's looking nice. Yeah, light's working. Turn the power off. And it's not green, so it worked. So, do you always need a state machine? Well, no, especially if you have really simple or linear logic or really very small and isolated components. It's not necessary for that. But when do you need a state machine or a state chart? Well, the rest of the time. Whenever you're modeling some kind of complex system, when you want to make it easier to document and debug and test, and when you need to be able to communicate your app logic to other people on your team and share that one source of truth. Everyone gets a better night's sleep with state machines. Here is the link again for my slides and the links to everything, the code and the demo and the talk. Enjoy that white noise machine. I apologize that the audio quality isn't better. And this QR code will take you to that link, which is noti.st/LAURAKALBAG/JICHVT. Thank you very much.